Hi, and welcome. We're going to discuss probability mass functions and probability density functions. What these are ways to contain all the information about our probability system. So, for example, a dice roll has some sort of it has outcomes and it has probabilities associated with that. And now with a probability mass function, mass because it's discrete, we can store all the information with the all the information about probabilities associated with each outcome. Okay, now let's just get down to it. What exactly are they? So first, there are two types of probability distributions. There's three. It's not mentioned here though. So there's two we're going to consider: a discrete and a continuous discrete and continuous probabilities. Now, for example, some cases of discrete probabilities are the number you roll on a dice. For example, the dice rolls discrete. You can go 1, 2, 3, 4, 5, 6. Another one could be number of Tinder matches you get in a week. That's discrete. You get 1 match, 2 match, 3 match, 4 match. That'll help you stick in your mind and remember. Or the number of times you're late to school or work this year, so you can count how many days you were late. Okay, some examples of continuous distributions. Continuous examples. So how long you have to wait in a queue before you're served. That could be once because you're measuring continuous time. The number of centimeters you grow this year. Because as long as you don't count it as like 1 centimeter, 2 centimeters, 3 centimeters, you count it as like all the decimals and all the fractions and stuff, like 1.26 centimeters, 1.7 centimeters, right? Centimeters, we're just saying like to measure things. And maybe the amount of time the bus is late, that is a continuous probability there. Continuous random variable, I should say. Now, we describe, as I said, we describe a discrete random variable with a probability mass function. So we call that PMF. We say that's PMF just for short, and that's given by this thing here, which just translates to the probability that x equals x. So the random variable equals some number. The dice, for example, I always like the dice. The probability that that should be a measure. That should be a bold p. My I'll fix that. So the probability that x, the random variable, equals some number like 2, for example, in the dice roll. So how about let's look at a example. So let's look at the Tinder example again. So you want to count like how many matches you get in a week. And let's say I'm not that good at Tinder, or whoever's in this example is, and you only get maybe like three matches maximum. 3 matches maximum per week. So you could say like a probability distribution, or probability mass function for this example. It could look like this. So you have P of x equals all these possible outcomes. So the probability, this tells us about the probability that if you get 0 Tinder matches, or you get 1 Tinder match, or 2 Tinder matches, and 3 Tinder matches, and here the probability is associated with it. So I've translated this in English here. Have a read, but we'll just pick one. So how does this information work? You say, okay, the probability of this probability mass function. What does it say? So in the first line, it says 0.2 if x equals 0. So this means that the probability I get 0 Tinder matches is 0.2. Or the probability I get 1 Tinder match in that week is 0.5. Probability I get 2 Tinder matches is 0.2, and so on. Then but you should also note a property of probability mass functions and also these density functions is that the probabilities all add up to 1. So if you you get all of that, it all equals to 1. So that means like you've exhausted the space. You've thought of every possible outcome. That's why it adds up to 1. Okay, so that's what that is for a a discrete distribution, random variable, and we'll just take a quick look at continuous ones. We'll do lots of exercises and examples so you understand what's going on. But here so for continuous random variables, think of waiting in a queue or something like that. So that's given by this density function. We call it a PDF, probability density function, PDF. Now, technically, it's not the probability that x equals x, because you can't. This is important. You can't think about a probability of a continuous distribution at a single point, because that's just 1, right? So it's like if I you consider a number line and you're throwing darts at the number line and you say, what's the probability I get a single number on the number line? It's 0, because there are infinite, like a full number line, not just 1, 2, 3, 4, 5, 6, but all the decimal numbers in between, right? So the probability you hit one single number is 0 because they're an infinite number. So that's, I guess, something to think about. So take home message: continuous distributions, you can't talk about this thing here. What you have to do is, we're going to introduce these distribution functions later, and we'll talk about how to calculate probabilities exactly. But for example, here I have an example. So let x be the amount of time in minutes that you have to wait for coffee. Then a possible probability, a possible PDF, of x is this thing here. So it says, okay, x represents the amount of time you're waiting for your coffee. X has to be greater than 0. You have to give it some support, some domain. So a support or domain just means like what possible values it could be. And then this represents your probability density function. So if we draw this, it looks like this. So let's make some space here. Okay, so let's say here we have bit messy, it's okay. So we have x and f of x, right? Now this is a decaying exponential. So what that is it looks kind of like this, right? So x, remember, is like the time you have to wait for your coffee, and it's saying like it's more like, so in these regions here, right at the start, so when it's more likely you have to wait for you'd have to wait for your coffee for a shorter period of time. But as we go further down the track of time, the probability decreases. So for example, down here, like this could be 2 minutes you have to wait, but this could be like 10 minutes you have to wait. So it tells us it's less likely that you are going to wait 10 minutes than 2 minutes, because up here the graph is higher. So we're going to discuss this later, but that's the general idea of probability, mass, and density functions. Now we have some ninja training to get on with. So try them on your own, but see, like this comes up again, and we're going to explain this more in detail. So try them on your own, see if you can do it. If not, just have a look at the solution videos. Oh, well, the solution videos are going to be the next thing. But anyway, we'll get straight into some ninja exercises.